Hello, ma'am.
Yes, sir, you can do it now.
Okay. Dhanlakshmi is not. Okay, Dhanlakshmi is there.
Sir, she will join.
Okay. Now, the fourth step in the extraction of the pure metal is purification or refining of the metal. Purification or refining of the metals. Metal obtained as above are usually impure. So metal obtained by pyrometallurgy, aluminothermite process, or by electrometallurgical process, or by hydrometallurgical process, all the metals are impure. It will contain impurities. So those impurities has to be removed. So the process in which the impurities are removed is called as refining of the metals or purification of the metals. Some of the methods used in refining of the metals are given below. The first one is poling, P-O-L-I-N-G. The molten metal is stirred with green logs of woods, freshly cut wood. So wood contains hydrocarbons. The wood at high temperature of the molten metal forms hydrocarbons like methane, which bring about the reduction of any oxide present in the metal. Now, for an example, now in pure copper metal, if copper oxide is an impurity, see, we are talking about copper, and copper oxide is impurity. Then what we do is, to this molten metal, freshly cut wood is immersed and stirred. When you freshly cut wood is immersed and stirred, what happens is this releases hydrocarbons. These hydrocarbons will bring about reduction. So this process is called as poling. So poling is generally performed for a metal whose metal oxide itself is an impurity, not only for copper. If we take gold, if gold oxide is an impurity, we can perform poling. If silver oxide is impurity, then we can perform poling. For iron, if iron oxide is impurity, then we can perform poling. So poling is a process in which freshly cut green wood is stirred with the molten metal. So when you stir the molten means semi-liquid state metal. When you say semi-liquid state, the temperature will be high. So at very high temperature, the wood will release hydrocarbons. These hydrocarbons will bring about a reduction of the metal oxide to metal. That's called as pouring. The next process is called as, next purification is called as cupellation. Now, cupellation is a process in which silver is refined. Now, what is this cupellation? The impure silver is heated in the presence of air. When we say impure silver, the impure silver will contain lead as an impurity. It will contain lead as an impurity. When you heat it in the presence of air, what happens is this lead, which is an impurity, gets oxidized to lead oxide. This lead oxide is called as litharge. Now, what happens? The silver contains lead as an impurity. Lead reacts with oxygen to form lead oxide. So when there is a large amount of air is blown, this lead oxide is also carried away by the air, leaving only pure silver. That process is called as cupellation. Silver is purified by a process called as cupellation. And remember, for competitive exam, silver contains an impurity, lead. That lead reacts with oxygen present in the air to form lead oxide, which is less denser, carried away by air. Followed with this?
Yes, sir.
Now, we are learning, these two methods are not there in the syllabus. This polling and cupellation is not there for your 12th standard exam. I taught you this because you may be required for some competitive exams. Now what we're going to learn, it will be there for your PUC. The next one is called as liquation. This is all there in your syllabus, liquation. Now what is this liquation? Now if I take a sloping earth like this, and if I have an impure metal placed here, this is impure metal, or it is called as crude metal. Now, in this impure metal, metal has lesser melting point than impurities. Metal has lesser melting point than impurities. Now, what will happen when you heat it? When you heat it, what will happen? Metal will start melting and flows. The impurities will remain here. This process is called as liquation. So liquation is performed to purify a metal in which metal has lesser impurity compared to the lesser melting point compared to the impurity. The process is used in refining easily fusible metals like lead and tin. The impure metal is heated on a slopy hearth of a reverberative furnace. Metal melts and flows down, leaving the impurity. That means metal should have lesser melting point compared to the impurity. That is why metal melts and flows down. Followed, and you should remember lead and tin is purified by a process called as liquation. Next is distillation. You know what is distillation? Separating the mixture based on their boiling points is called as distillation. Right? Boiling point, you know what is boiling point also. So separation of metals or any elements based on their boiling point is called as distillation. Here, by distillation, some metals have low melting point and soon vaporizes on heating, while associated impurities remain in solid state. Some metals have very low melting point and soon vaporize on heating, while associated impurities remain in the solid state. Zinc, mercury, and arsenic are purified by this method. Vacuum distillation gives very pure product and used in the refining of the metals of 1A and 2A. This is generally for metals like zinc, mercury, and arsenic. Now, fractional distillation. The process is applied for separation of cadmium from zinc. In metallurgy of zinc, metal is invariably associated with cadmium. So in the extraction of zinc is invariably associated with cadmium. To remove this cadmium, what we do is we perform fractional distillation. The impure zinc is mixed with powdered coke. Impure zinc is mixed with powdered coke and heated. When the first portion of the condensate contains cadmium, while zinc is obtained in the subsequent process. That means the first portion which comes out, because the boiling point of cadmium is lesser compared to zinc. So cadmium gets distilled first and zinc comes out later. So that's called as fractional distillation. Separating components, mixtures based on the boiling point is called as fractional distillation. Next, if you observe thermal decomposition. Now, we have to learn in detail about this thermal decomposition. This is very important. In thermal decomposition, we have something called as, no, not the thermal decomposition. Yeah, we can mention it as thermal decomposition, or this also can be referred as vapor phase refining. It also can be referred as vapor phase refining. So that means purifying the metal in the vapor state is called as vapor phase refining, or it's also called as what? Thermal dissociation. Now, in thermal dissociation or vapor phase purification, vapor phase, purification of the metal in vapor state, purification of the metal in gaseous state is called as vapor phase refining. In that, we have first Mons process. Now, what is this Mons process? Nickel is heated with carbon monoxide, impure nickel. Now, this impure nickel, when you heat it carbon monoxide, we will get a complex called as nickel tetracarbonyl. So this heating is done around 60 degrees Celsius, around 60 degrees Celsius. So you get nickel tetracarbonyl, NiCO4 times. Now this nickel tetracarbonyl, if you heat it to 150 to 180 degrees Celsius, this nickel tetracarbonyl will decompose to give nickel, giving you carbon monoxide. This nickel which is obtained is pure nickel. Impurities will be carried away along with carbon monoxide. This is an example for purification in water vapor phase, and this process is called as Mons process. Mons process is applicable only for nickel, remember. Did you understand Mons process?
Okay. Yes, sir.
Yeah, now we also have the second method that is called as Van Arkel process, Arkel or Arkel process. Now it is similar. Now what is that similar? Now this is done for zirconium and titanium. Zirconium is heated with iodine. I don't remember the temperature. This is T1. We will note temperature T1. Zr, it is not Zn, zirconium is heated with iodine. So we get zirconium tetraiodide. It's a complex. Now this zirconium tetraiodide, when you heat it to a higher temperature, much higher temperature, so what happened? This decomposes to give zirconium, giving you iodine back. This zirconium is pure, and impurities gets eliminated in the form of, along with iodine. Likewise, titanium is when heated with iodine at lower temperature, we get titanium tetraiodide. This titanium tetraiodide, when you heat it to very high temperature, you get titanium with the liberation of iodine, and this titanium is what? Pure. These two processes is also called as Van Arkel process, and it is also an example for vapor phase refining. Purification in vapor state is called as, see they are mentioned, Mons process and Van Arkel process they are mentioned. They don't mention the temperature, but temperature in your 12th CBSE textbooks, it will be there. Please note down the temperatures. It's important question. Now coming to the one more method of refining, it's called as electro refining. Now this is also important. I will erase this vapor phase refining, Mons process and Van Arkel's process. We will go to electro refining process now. Now, what is this electro refining? In case of electro refining, the impure metal, see, electro refining, the name itself, electro, it's happening in the presence of current. So you take an electrolytic cell. In this, thick impure metals are made as anode. Thick impure metals are made as anode. Anode is a positive electrode. Remember, it's a positive electrode. And thin pure metals are made as cathode. Thin pure metals are made as cathode. Cathode is a negative electrode. And these two electrodes are dipped in an electrolyte. Now assume copper, impure copper, and these are pure copper. Thick impure copper metals are connected to anode, positive terminal. Thin pure copper are connected to negative terminal, and these are immersed in the electrolyte. The electrolyte is copper sulfate. In case of copper sulfate, we know that it will dissociate to form copper 2+ and SO4 2 minus ions. Now, what happens on passing current? Oh, sorry. On passing current, can you see the screen? Can you see the screen? Hello?
Sir? Sir,
Can you
didn't
see the
understand, sir?
Can you see the screen?
No, sir. No, sir.
No?
No, sir.
Okay. Yeah. Now I think you should.
Yes, sir. Now is it?
No, this systems, no problem. All right. Anyways, now thick impure metals are made as anode. Thin pure metals are made as cathode. That is, thick impure metals are connected to positive terminal. Thin impure metals are connected to negative terminal. These electrodes are immersed in the electrolyte. So what happens? We all know that at anode, oxidation takes place. What is oxidation? Oxidation is loss of electrons. So thick copper, which is an anode, will lose electrons to form Cu2 plus ions. Now what happens? This will decompose to give you what? Cu2 plus ions. Now the Cu2 plus ions will move towards cathode. When it moves towards cathode, at cathode, what takes place? Reduction takes place. Reduction takes place. So you get copper. So what happens? Now this copper ions gets deposited on what? Your cathode. It gets deposited. Are you following what I'm drawing and showing you? Not clear, but able to understand?
Yes, sir.
This process is called as electrorefining. During this electrorefining, at anode, there will be some mud deposited, and that mud is called as anode mud. It's called as anode mud. This anode mud, MUD mud, contains some noble metals like gold, silver, etc. So this is important. If I'm taking gold, thick impure gold, thin pure gold, and if I use gold chloride as an electrolyte, what happens? Thick impure gold will undergo oxidation, and the pure gold will get deposited here. So you can refine, electro-refine gold also, silver also. So that's the advantage of electro-refining. Any metal can be refined. Now, the last method of refining we have, that is called as zone refining. That is called as zone refining. The zone refining, it's also called as fractional crystallization. Generally, this fractional crystallization or fractional zone refining is for semiconductors like silicon and germanium. Silicon and germanium can be purified, or gallium can be purified using this method. The process is called as zone refining or fractional crystallization. Now you can see there's an impure metal taken. This is an impure metal. This whole block is an impure metal. So what happens is, now elements such as silicon, germanium, gallium, etc., which are used as semiconductors, are refined by this method. Highly pure metals. So 99.999% purity you will get by zone refining. This is called as ultra pure metals. Ultra pure metals. Ultra pure metals are obtained by zone refining. Remember, ultra pure metals are obtained by zone refining. So highly pure metals are obtained. This method is based on difference in solubility of the impurity in molten and solid state. So solubility of impurity in solid and molten state will differ. That's the principle of zone refining. The method is based on difference in solubility of impurities in molten and solid state. Now, a movable heater is fixed round the rod of the metal. The heater is slowly moved across the rod. The metal melts at a point of heating, and as the heater moves on from one end to the other end of the rod, pure metal crystallizes while the impurity pass on. The impurity pass on. Now on the adjacent metal zone. Now, what happens? Now, to understand this, there's a diagram represented, but anyways, we will draw and make you understand this again, zone refining. Now, we take an impure metal here. This is an impure metal. In this impure metal, at this zone, at this part, you heat. When you heat at this part, what happens? The metal starts melting here. The metal starts melting at this part. Now, from this part, you shift the heater. You shift the heater to the other, I see what happened. Shift the heater here to the other position. So what happens? Impurities will move towards the hotter region. So pure metal will be left here. This is pure metal. This is impure metal, sorry, impure metal. Oh, so that means impurity will be in what? The molten state, impurity. And pure metal will be here. Similarly, keep on moving the heater, different positions. All the impurity will be accumulated at one corner. Now you cut this off and remove the impurity. And this metal, what you get is an pure metal, ultra pure metal. Did you understand this? So you are purifying the metal part by part. Therefore, it's called as zone refining. So when you heat, the metal starts melting. See, the impurity and the solubility of impurity in molten and solid state of the metal differs. So impurity will be here in solid state because it is getting cooled here. But on heating, the impurity will flow to the cooler region. Therefore, you get the metal which is pure. And thus, metal what we get is called as ultra pure metal. Did you follow this? All right. Followed?
Yes, sir.
Is the screen visible?
Yes, sir. Visible, sir.
Now, summary of the extraction of metals. The summary, you can just go through this slide, will be available in the video. So we are now going to learn about the slide again. Now, this is important. Metallurgical processes. We need to learn the metallurgical processes. Right? Something happened with my notes. Something happened with my notes. Something happened with my notes. Right. Metallurgical processes. Now, I clearly mentioned different metallurgical processes. I clearly told you what is pyrometallurgy, what is electrometallurgy, and hydrometallurgy. So pyrometallurgy is extracting a metal at very high temperature as far as pyrometallurgy. Extraction is done using heat energy. Metal like copper, iron, zinc, lead, tin, chromium, mercury, these all are extracted from their oxides by heating at a high temperature, called as pyrometallurgy. Hydrometallurgy, extraction of metal involving aqueous solution, is known as hydrometallurgy. Generally, noble metals like gold and silver are extracted by hydrometallurgy. Hydrometallurgy is a process of extraction in solution state. Extraction of metal in solution state is called as hydrometallurgy. Next, we have electrometallurgy. I told you highly electropositive metals, first and second group elements. Extraction of highly reactive metals, highly electropositive metals, like sodium, potassium, calcium, etc., by carrying electrolysis of one of the suitable compound in fused or molten state. So, extraction of metal by the principle electrolysis is called as electrometallurgy. Electrometallurgy is applicable for highly electropositive metals. Now, coming to furnace. In the extraction of metal, different types of furnaces are used. Each furnace has its own characteristics. Some principles furnaces have been described below. We have mainly two types of furnace. We are not going into the details of the furnaces. First one is a blast furnace. Now, this blast furnace is a vertical furnace. So, vertical furnace, a furnace which is vertical is called as a blast furnace. Now, next we have a reverberatory furnace, horizontal. It will be horizontal. The furnace which is horizontal is generally called as a reverberatory furnace. Next we have is electric furnace. Electric furnace, and fourth we have muffle furnace. We don't have to learn all the different types of furnaces. For you to understand, remember, one is blast furnace, the other one is reverberatory furnace, and the next is electric furnace. Now coming to the extraction of metals. Now, extraction of metals, I will share a different slide in the class. All right. Where is that sharing of a news there? Yeah. Can you see the screen?
Yes, sir.
Yeah. So we learn some of the extractions and we learn the questions of this chapter later. These things you have in your syllabus to be learned. So we use the same thing. What's wrong? Where is this? All right. So now we learn some important extractions. That is, we learn the extraction of iron. And then we will learn copper, which is there in your syllabus. And then we will learn about zinc also. Now, extraction of iron. Iron is extracted by the blast furnace, using a blast furnace. Iron is extracted from hematite. Remember, it's important. Hematite, hematite. Iron is extracted from an ore called as hematite. Now, hematite is Fe2O3. The molecular formula of hematite is Fe2O3. Now, this hematite, along with coke and limestone, hematite, Fe2O3, coke is carbon, limestone is calcium carbonate. In the ratio 8:4:1 is dropped into the furnace. This combination is called as charge. This combination is called as charge. What is charge? In the extraction of iron from hematite, coke, and calcium carbonate in the ratio 8:4:1 is called as charge. The charge is passed through the blast furnace. You can see this is like a cup and this is like a cone. This arrangement is called as cup and cone arrangement. It's called as cup and cone arrangement. Because the pressure created in the blast furnace will be extremely high. To withstand that pressure, we need to have a special type of lid, something called, that's called as what cup and cone arrangement. You can see this is in the form of a cup and this is in the form of a cone. So charge is passed into the blast furnace through a cup and cone arrangement. Now you can see in the blast furnace, we have refractory bricks. These refractory bricks are also called as fire bricks. This is made of calcinized dolomite. Now it's a combination of calcium carbonate and magnesium carbonate. Now this furnace is made of steel. Steel at 1600 degrees Celsius will melt. Therefore, we are using something called as refractory bricks or fire bricks. It's nothing but bricks, which can withstand very high temperature. It's made of calcinized dolomite, calcium carbonate, and magnesium carbonate. Now, charge is introduced through cup and cone arrangement. So what happens? There are 5 steps in the reaction here, 5 reactions taking place. The first step of the reaction is called as zone of combustion. The first one is called as zone of combustion. We know that combustion is burning something in the presence of oxygen. So what happens is coke, which has been passed through the charge, coke is burnt in the presence of oxygen to form carbon monoxide. So 2 moles of coke. This is a zone of combustion. This is zone of combustion. Now, this is the hottest part in the flame, in the furnace. The temperature is around 1600 degrees, close to 2000 degrees Celsius. Now, what happens is carbon dioxide is formed. Complete combustion will take place here. Carbon dioxide is formed. And the energy given out is very high, 1600 degrees Celsius. Now, the second step is zone of fusion. Now, what happens is this carbon dioxide, which is formed, will react with unreacted coke to form carbon monoxide. This is an exothermic process. Energy is very high, and this zone of fusion is an endothermic process. Therefore, you can see temperature decreases from 1600 to 1300 degrees Celsius because it's an endothermic process. Did you follow? The first step in the extraction of iron in the blast furnace is zone of combustion. Carbon burns with oxygen to form carbon dioxide. You can see oxygen is passed here. Hot air is passed here for oxidation, hot air. And it's called as tires through which hot air is passed. If air is not passed, combustion will not take place. So coke gets combusted in the presence of oxygen to form carbon dioxide, liberating enormous amount of energy. Now, carbon dioxide is a gas. It will move to a cooler region. When it goes to a cooler region, this carbon dioxide reacts with unreacted coke to form carbon monoxide. It's an endothermic process. This zone is also called a zone of absorption also. They say instead of zone of fusion, they can call it as zone of absorption also. Now, the third step is zone of slag formation. Zone of slag formation. Now, what is the zone of slag formation? Limestone is calcium carbonate. This limestone will decompose to form calcium oxide, liberating sand. Liberating carbon dioxide. Liberating carbon dioxide. Now, calcium oxide, which is formed, will react with, this is a flux. And the impurity is sand. Silica is an impurity. It's a gangue. So flux and gangue gives you slag. So slag formed this calcium silicate. This calcium silicate will be formed in the region around 800 to 1000 degrees Celsius. Calcium silicate will be formed. This is the third zone. Now, the fourth and the important zone is zone of reduction. The fourth reduction. I'm going to teach you an important question here. Three important questions we'll be learning. No, two important questions. 1 marker we'll be learning here. As a whole, this reaction can be asked for 3 marks. Now, zone of reduction. Hematite is Fe2O3. Now, you can see here, carbon monoxide is formed. This carbon monoxide will react with hematite, will reduce hematite to form iron, giving you carbon dioxide gas. So iron is formed here at around 800 or 600 degrees Celsius. Reduction takes place. So iron being heavier sinks down and comes out as a molten metal. Slag, which is formed here, next it forms a second layer. So slag comes out of this, and the metal which is heavier comes to the bottom, and it can be removed. So now they can ask you, what is the reducing agent in the extraction of iron in the blast furnace? The reducing agent in the extraction of iron in the blast furnace is carbon monoxide. It is not coke. Remember, it is not coke. It is not coke. Then what is the function of coke? The function of coke is the coke acts as fuel. It gives energy. You can see 1600 degrees Celsius, zone of combustion. Coke gives energy to the blast furnace. So coke acts as a fuel in the extraction of iron in the blast furnace, and carbon monoxide acts as the reducing agent. Now, the iron which is formed here, it's called as, it is the impure form of iron. Percentage of carbon will be more in this iron. This will be called as pig iron. It will be called as pig iron, or it will be called as cast iron. So we can vary the percentage of iron present here, and then we can get different types of iron. So this pig iron, which is formed here, this pig iron, I'll erase this and write. The pig iron which is formed, or the impure iron which is formed here, it contains around 4% carbon. It contains around 4% carbon. Now, this pig iron can be converted to cast iron. This is first one, pig iron. A pig iron can be converted to cast iron by heating it with, by heating pig iron with scrap iron and coke. So when you heat the pig iron with WITH, with scrap iron and coke, the percentage of carbon decreases to around 3%. 3% carbon. From 4%, it decreases to 3%. It is hard and brittle. This cast iron is converted to, the third one is called as converted to wrought iron, ROUGHT, wrought iron. This is the purest form of iron. Purest form of iron, which contains about 0.2 to 2.5% carbon. So the percentage of carbon in the wrought iron is very less. So there are 3 types of iron. So the first iron, what we obtain in the extraction of iron by using the blast furnace, is called as pig iron, or it's called as pig iron. It's called as pig iron. This pig iron contains around 4% carbon. This pig iron can be converted to cast iron by heating it with scrap iron and coke. in the blast furnace. So around 3% of carbon will be obtained. That's called as cast iron. This is hard and brittle. And wrought iron is the purest form of iron, which contains around 0.2 to 2.5% carbon. It is soft, malleable, and ductile. It is prepared from cast iron by oxidizing the impurity. So cast iron contains 3% of copper. When you oxidize, when you heat it in the presence of oxygen, carbon gets eliminated as carbon dioxide by decreasing the percentage to around 0.2 to 2.5%. Therefore, you get wrought iron. This is malleable and ductile. You know what is malleable and ductile. Maybe possibly we will learn in the tomorrow's class, we will learn about something called as Ellingham's diagram, and we also can learn about the extraction of copper and zinc, all that in detail. We will learn in the tomorrow's class. Ma'am, I'll stop the class, ma'am.
Yes, sir.